Got a no AC call out here and absolute rat's nest of wiring, and of course the wiring schematic was gone like 20 years ago. I have it jumped out with this 4-way jumper, by the way. Make yourself one of these. You can take them apart and you know, just work normally, or connect them so you can jump out a bunch of things. Anyways, I've traced out this absolute mess to the contactors not getting common. So I got kind of an interesting thing that I'm going to do here, because the common actually runs back up in here and is buried back in there. Alright, so from ground I have my amp clamped around there, and I'm running this down to this power resistor that I made. I think these are 220 ohms. I don't know exactly, but obviously I've made it for low voltage only, but draws about an amp of current if you're on a power. So if I go on here, I guess a little less than an amp. So I'm right on red. Well, what's going on? What I need to know, so I've got 24 volts in and 24 volts out. Obviously, because my common is not being connected back to the transformer common. But what I need to know is, see, when I get back there, am I on the power? Am I on a power? Or am I on a common that is being backfed power through the contactor coil? So if I go right here, you can see my amperage is less because I'm in series with the contactor coils. So right back here, I'm at 6.4, and then it drops down to 5.4. Okay, so I'm going to go back into that economizer section and start probing around and see where my missing common is. It does look like it's 220s in series, so make it 40. All right, let me get set up. All right, so let's try one out. Thinking this red here is probably a full-time power supply, and it is. So I'm going to go down here and figure out which one of these is a common that is backfeeding through the contact. 24 volts. Normally I would cut this fan off here, but if this isn't running, then it cuts out the Y calls. But our black wires are running down very deep in there, and there's no access to the freestat. I just pulled the wires off and got the transformer rescue fuse out here, and you can see that is my common. So if I take this right here and jump it on the ground, my compressors should come on, and they just did. Hopefully you can hear that. So jumping this to ground is a great way of testing, you know, that this is for sure my wire, which I suspected it was anyways. But of course, maybe there's something else going on in the circuit, so let's just bypass. I mean, looking at the wiring, I'm pretty sure there's not, but to be 100% sure, let's just jump this out as if we had a closed freeze stat and see what happens. So I don't know if you can hear that, but the compressors are running. So yes, for sure the freeze stat. So just wanted to add that right there, because technically, you know, that maybe there was something else going on, but I didn't think so from looking at the wiring. I realized that there were a lot of wires, and to be fair, that unit was just unbelievably bad. I mean, such chaos. The wiring colors were really, really hard to make out. Everything was tucked up near the high voltage, just horrible. But anyways, let me do a recap, because I don't want to leave anybody really confused about what I was doing there. So what I found was that I had my 24 volts going to the contactor coil, right? And then, so I measured with my meter from here to ground, and the reason that this was okay to do is because the common on the transformer was bonded to ground. So anytime that that's true, you could reference ground for your measurements. So I had 24 volts here and here. So what does that mean? All that means is the common is open somewhere, because the 24 volts is going through here and through the coil out to the other side of the contactor. As soon as the common makes its way back, then your voltage is going to drop across this coil, and you'll have 24 volts here and 0 here. Hence, if you measure across, you get your 24 volts, right? Okay. Now the problem is, this break in the common I knew was not close by, and again, that wiring was very difficult to trace out. So when I was going back to the back of the unit and I had that connector with all of those wires in it, the problem with the meter is it doesn't put a load on the circuit. So 24 volts here looks the exact same as 24 volts here, as 24 volts here, you know. But if I take a power resistor like this, I've just got these in series, and I take it and I have it on ground, right? So up here, I've got that on ground, and then I'm poking around here. If I go here, then I'm going to get full voltage to the power resistor and full amperage, right? But if I come down here and poke right here, then I'm not getting full voltage, because some of that voltage is dropping here and then the rest of it's dropping here. So my amperage goes down. So what that allowed me to do is go back in this connector and see, all right, is that full power? And it was like, yes, 0, 0, 0, full power. So I went through that connector, and I couldn't find where I had a common that had 24 volts on it. So then that led me back and ended up pinpointing it as the freestat. But this can be a really, really helpful thing, and I'll show a couple different ways of making something like this here in a minute. But it's not just that. It's like it's not just for what I just showed you. It's like, you know, let's say that you have 24 volts coming from the thermostat to the contactor, and you have a good common. You take this wire off and you measure it, and it's 24 volts. You put it on there, but it's not energizing the contactor. Well, what you can do is you can take this and start loading the wire and start going upstream and seeing, okay, where do I get full power and where does it drop out? And it's going to drop out downstream of that resistance. Hopefully that makes sense. But so this is one of my favorite versions. And if you're wondering, you know, you can really underestimate 24 volts if you've never put it through a resistive load. It can get unbelievably hot, hence the need for power resistors. And even these, if left on too long, will get hot enough to where you can't touch them. So just be warned. Here's another way to do it. Take like a 100-watt light bulb and use that as your load, and that bulb will get hot as well, so you got to watch that. This, if you have a hard time ever reading some kind of amperage, like off of this or off a 100-watt light bulb, you can either loop this wire around more times on your meter, you know, or just hook up something like this. And this is 10 loops of wire, so whatever current you read on your meter will be times 10. So you just move that decimal point. So if you're reading 2.0, that would be 0.2 amps. And this can be really helpful for amp clamping, you know, things like gas valves and stuff that's just really hard to get a read on. A loaded circuit test. There are so many advantages to doing loaded circuit tests for diagnostics. I cannot emphasize it enough. In fact, hang on a minute. It's so important to me that I actually made a test light for 24 volts. Now, you can run an automotive test light on 24 volts, but it's really hard on the bulb. So I just got a diode in there. It doesn't matter which way you put it. Obviously, you're just cutting out 1/2 of the sine wave, and it is a little goofy because I've got my adapters I made so you can put multimeter ends in there. But this is another really great way of identifying, do you actually have 24 volts, or is it going through some resistance and then out the other end? However, I didn't even get this out because I suspect it's probably not enough of a load to show a difference in the light, but still very useful for you know, poking around in control wiring and getting an idea of what's going on. All right, hopefully that was educational, and hopefully this cleared up any of the confusion around what I was doing there.